As you know, the phenomenon of photoelectric effect explains that light consists of packets of energy known as quanta, and this characteristic of light exhibits during its interaction with matter. Each such packet has energy E equal to h nu, where h is the Planck's constant and nu is the frequency of light that is being used. Einstein concluded that each packet of energy can also be associated with the definite momentum P equal to h nu by c, where h is the Planck's constant, nu is the frequency of the light used, and c is the velocity of light. Each quanta has definite energy as well as momentum, and hence each packet of energy can be treated as a particle, which is called photon. Now we can say that light possesses a particle nature as well. In 1924, A. H. Compton proved the particle nature of light with his experiment on scattering of X-rays from electrons. The phenomena of scattering of X-rays from electrons is called the Compton effect. Let's now summarize the properties of photons. In the interaction of radiation with matter, like in the case of photoelectric effect, it seems as though radiation is made up of particles called photons. Each photon has energy E equal to h nu. Since nu is equal to c by lambda, we have E equal to hc by lambda, where lambda is the wavelength of light used. And momentum P is equal to h nu divided by c. All photons travel with the same speed of 3 × 10⁸ meter per second through vacuum, irrespective of their frequencies. All photons of light of a particular frequency, nu, or wavelength lambda, have the same energy and momentum, irrespective of the intensity of radiation. An increase in intensity of radiation of a given wavelength implies an increase in the number of photons crossing per unit area per second, as long as the frequency of radiation is constant. Hence, all the photons of a given frequency still have the same energy and momentum, irrespective of the intensity. The rest mass of a photon is zero. Photons pass undeviatedly through an electric field, which can be created by the charged plates of a capacitor. Hence, we can say that photons are not affected by electric field, which means they are electrically neutral. The photons also travel undeviatedly in the region between the two magnets, and so they are not affected by magnetic fields as well. In a photon-particle collision, such as photon-electron collision, the total energy and total momentum of the system are conserved. However, the number of photons may not be conserved in such a collision. This is because the incident photons may be absorbed or new photons may be created. In the case of photoelectric effect, we have seen that the photon is completely absorbed in the process of photon-electron collision. When X-rays are scattered from electrons after the photon-electron collision, a new photon is created.